Thank you very much for the kind introduction, and I welcome everyone to this presentation on shade-resistant modules, cell technology versus module technology. Before starting the technical presentation, I would like to shortly introduce our company. AE Solar is a PV module manufacturer with 2.2 gigawatt production capacity in Turkey and China. We are present more than 20 years in the market in over 100 countries. We are also recognized by PVEL and PV Magazine as one of the top performers in the area of performance and reliability. So here you can see an overview of our portfolio. So as you see, apart from modules with different cell technologies that they are standard modules, we are also highly focusing on customized modules for different applications. This means modules for vertical PV, for agri-PV, BAPV or building attached PV, carport PV, and our signature shade-resistant PV module, which we are bringing the second generation in 2026. We have also started to do a collaboration with a BC manufacturer as an OEM partner to bring also IBC in our portfolio. So let's move into the technical part. In Europe, almost 60% of the modules are on the roofs, around 30% residential and 30% commercial. For example, in the case of Germany, almost 60% of the modules are on the roof, and in Netherlands, as the biggest market per capita, almost 80% of the modules are on the roofs. However, modules on the roof have some challenges. First of all is the limited area on the roof, and second, that the modules on the roof are not always 100% exposed to the sun. So this means building elements or neighboring buildings can cast shadow on PV module, which can influence its performance. Well, when the module is shaded, it loses power drastically. Just to give you an impression, only 5% shading of the module area in critical points can lead to the total shutdown of the PV module. And of course, continuous partial shading can lead to hot spots and in the worst case, also fire. Well, to give you an kind of overview that how this works, and actually Dr. Sun gave also a very nice introduction to my presentation, solar cell produce energy in forward bias. So this is the green area that you can see on the chart. But when the solar cell is shaded in the module, it has a lot of negative voltage, and it also starts to work in reverse bias. So instead of producing energy, it consumes energy. And as you can see, the amount of energy consumption in this area is significantly more than the production. So here, what defines how much energy is being dissipated in the solar cell is the point that the solar cell electrically breaks down, which is called reverse breakdown voltage. So we looked into 4 different cell concepts. Our old-timer aluminum back surface field, PERC, TOPCon, and BC. And we looked into the reverse breakdown behavior. As you can see in aluminum back surface field, the solar cell breaks down somewhere around minus 14 volts. But there is a high irradiance dependence range between minus 5 to minus 13. This means in higher irradiation, the solar cell breaks down faster. In the PERC solar cell, the reverse breakdown voltage is somewhere around minus 20 volts. And we see again a high irradiance dependence range between minus 5 to minus 21 volts. This means again, when the solar cell breaks down, it consumes a lot of power. Because for us, it's very interesting, either the solar cell breaks down very fast or very late. Well, with TOPCon, we come to one of the situations. So we see that it breaks down in minus 39 to minus 48, but it has significantly lower irradiance dependence range, which is also somehow delayed, and it's between minus 20 to minus 48. So here irradiance dependence starts quite late, means that up to minus 20 volt, we somehow, in the highest irradiation, the solar cell still works like a diode. But the king is back contact. So as you can see, it breaks down somewhere around minus 4.5 to 5 volts, and it is significantly lower than the other solar cells. And here we see almost no irradiance dependence. So as you can see, even in higher irradiation, the solar cell performs the same in reverse bias. So this is also very interesting because it means that the solar cell breaks down faster and therefore it has less energy consumption and less heat dissipation. So this you can see also in this nice picture from ICO and also a nice test setup outside that you can check the results. Well, but now let's look into module technology. AE Solar launched the first generation of shade-resistant PV modules in 2018. Here we had one bypass diode per single solar cell that we placed the bypass diode in cell spacing on one ribbon. So we had integrated bypass diode for almost 63 bypass diodes, and it had to work up to 6 busbar solar cells because up to that point we had still ribbons and not wires. And okay, it was also a reliability challenge for this panel with so much diodes, but on the other hand, we saw a super performance. So we did the indoor shading test with Fraunhofer CSP. Also, we did some outdoor test with Anhalt University of Applied Sciences. But here you can see the indoor test results for the module compared to a standard module. When we shade the solar cell for one cell, as you can see, it loses only 3%, whereas the standard old module would lose 1/3 of its power. And in a little bit more extreme case, in case that we would have shaded the bottom row of the module, a standard module would lose 100% of the power, whereas this module would lose only 20%. However, with the half cell technology and also more bus bars, we had to come up to a new idea. So we started to look into some possibilities to make new modules, and we had to consider some criteria. So we had to consider that we have to remain with the same glass size so we don't have problem with the supply chain. And meanwhile, we had to reach as close as possible to the peak power of the standard or competitor modules. It had to look pleasant, so aesthetically, and also it had to perform a good reliability and durability. We had to also consider that it's cheap to implement and fast to produce. So we simulated around 150 designs, and from this 150 design, we chose 5 prototypes, and we built modules out of them, and we sent them to Fraunhofer CSP for indoor shading test and reliability test. We also compared them with the reference module with butterfly design with TOPCon solar cells and also back contact cells. So here you can see an overview of shading scenarios we did. So we considered 9 different scenarios that we are shading the solar cell, one solar cell, one row of cells, and one column of cells. We also considered it in different direction, left to right, bottom to up. And also we considered multiple rows and multiple columns and also diagonal shading. So for the sake of time, I will only show 3 of the scenarios. So here you can see the first scenario when we are shading only one solar cell. You see that the TOPCon butterfly module loses the power, 1/3 of the power immediately. Whereas the back contact module performs better, but the best performance was from our shade-resistant modules, all 5 prototypes, which were over 95% of the nominal power when the module was shaded. The second one was a bit more critical. So we see that in this case, back contact module and standard TOPCon module, they perform somehow similarly. Whereas our modules perform again, way better than these two scenarios, but two modules. But of course, since they have different designs, under this shading scenario, they also perform differently. And finally, row shading. So here you can see that, again, back contact and butterfly perform similarly because the diode kicks in and basically bypasses the string, whereas the other modules perform, again, better compared to the standard butterfly module design. So here is an overview of this all 9 shading scenarios. You see that this is a kind of gain compared to the standard TOPCon module with butterfly design. We also put the back contact module for the comparison. So you can see that in some scenarios, back contact solar module also performs nicely. But in all cases, the designs that we considered outperform the back contact module by far. But all of these modules, of course, outperformed the standard module with TOPCon solar cell and butterfly design. In some cases, and in some scenarios, we even could reach up to 70% better performance. But we have to use diodes in the module. Of course, it should be placed in different locations and with different quantities, but we considered different type of bypass diodes. We considered passive bypass diodes and active bypass diodes. So the difference is, again, heat dissipation, because this is a topic, not only for solar cells, but also for bypass diodes. So we built one module with passive and active bypass diode. We reverse biased them. We injected current with the value of short circuit current, and we measured the temperature. So as you can see in the module with active bypass diodes, you could notice some of the bypass diodes, but in the active bypass diode sample, you cannot notice any diodes. But I can assure you the diodes are there. So we measured up to 70% lower temperature compared to the passive bypass diodes. We are at the moment also doing the outdoor shading test on the rooftop of Fraunhofer CSP in Germany, and we have our prototypes plus a standard module with TOPCon solar cell and back contact solar cell as a reference in the same shading scenarios. So the results will be also published very soon. But now, let's have a look to the economics. According to the research from Zurich University of Applied Sciences, when you are using shade-resistant modules, you don't need to use power optimizers. So here, this means that the cost of the system can be lower. We also should notice that it was also a discussion yesterday that the customer buys the module in euro per kilowatt peak. So they buy power. But what they really need is energy in euro per kilowatt hours. So in case that the module is shaded, it doesn't matter what is the power or efficiency. It produces nothing or produces very small amount of energy. In case that you are using shade-resistant modules, so first of all, you save some cost from the system because you don't need optimizers, and meanwhile you produce higher energy yield, which can contribute to a lower levelized cost of electricity at the end. So a takeaway message is that the module design is important as much as the cell design, and I would say that it's even more important. So shade-resistant modules offer a good energy yield and also economic and profit margins. Now, in case that we look at the solar cell technology, BC is by far the best solar cell we can use for shade-resistant modules. It has lower breakdown voltage, it has no irradiance dependence, and it has lower power dissipation compared to, and temperature when it is shaded compared to the other technologies. TOPCon is also a good choice, but after BC. So we are doing it at the moment with TOPCon because we cannot make BC yet, but we will see in the future. The module technology, I think, is the key answer. So module design outperforms the cell technology advantage. And we could achieve up to 70% better performance under shading in specific shading scenarios. And we of course need diode, and for the diode we went in the direction of active bypass diode because it showed significant advantages in the terms of losses and reliability. However, what is a superb shade-resistant module? A superb shade-resistant module is a module with back contact cells and a proper module design. And with this, I would like to thank you very much for your attention.